Now, moving forward with the canonical ensemble situation where the temperature is constant, we know that there is a system and then there is a temperature reservoir as you are seeing on your slide right now. So, the system is connected with the reservoir, which is supplying this resistance term or additional heat or subtracting heat in order to keep the temperature constant. And if you look at kinetic energy, feedback makes 3 by 2 k T, which is what we are looking in terms of the distribution of the term, which is coming from equipartition. So, if you look at now what is the effect of thermostats. So, thermostats are essentially starting the original vibrations of the system. Again, we look at the harmonic oscillator, it is oscillating with certain kinetic energy, and if you distribute that kinetic energy with the initial velocity, then you know that entire system is vibrating with certain frequency, and if you add all those vibrations together, that comes up with the thermal energy, and that then converts into the temperature of the system from the perspective of the equipartition theorem, where that is where the kinetic energy is distributed into n number of such particles. So, when you provide this damping force, just like in a damped vibration, the resistance term is essentially taking the temperature oscillations into a particular oscillation which conforms to particular temperature. So, if you look at on your slide, now we look at the implementation of such algorithm. So, you have number 1, time step q is equal to 1 and time step q is equal to 100. So, initially it starts violently and then slowly it damps down, and this is where we say damped vibration. And so, it is almost similar to that. However, this is showing the change in the amplitude of the temperature and its fluctuation over a period of time. So, now if you look at a certain point, it will become constant. If you look at further down, now it is the temperature is close to 1.725, and that is where you can draw this red line at the center, and you can see the fluctuation, the sinusoidal fluctuation around that temperature. So, now you have a thermostat which is set at 1.725 reduced temperature. So, if you look at the dimension on the left hand side, there is a simple input for this program. So, you are providing dimensions, type is argon atom, potential is argon potential, density is 1.05, temperature is 1.15, and then you are looking at the length, time length. So, if you look at the lattice, which is FCC, and we are providing different kinds of seed with that understanding, and if you look at this particular situation, then the thermostat becomes constant. So, with that understanding, now we say what is the effect of thermostats in MD calculations. Number 1 is thermostats are needed in non-equilibrium situations. So, if you have a system which is violently going up and down in terms of temperature and you want to bring it to the equilibrium situation, then you need thermostat, because if you are going to create a TVN ensemble where temperature is constant, that means you are bringing the system to equilibrium state where the temperature is constant with respect to time. So, in that case you need a thermostat and as you remember, molecular dynamics requires equilibrium to set up, because we are using ergodic theorem, which is only applicable or can be applied if the system is in equilibrium. So, the time average will become ensemble average and vice versa only if there is a what we say quasi static equilibrium or equilibrium situation. So, the thermostats are very important to bring in that equilibrium status, and if you also want to make molecular dynamics as a time reversible and you want to make it deterministic, that is another situation where you do need the thermostats, so that you can follow that trajectory in a canonical distribution. So, TVN ensemble can only be projected or simulated if we have a thermostat. Now, how natural are these thermostats? Is that an artificial thing that we are putting into the simulation? Is that creating a lot of effects? So, if you look at in this case, we are the thermal bath is interacting with the molecules or atoms in a velocity and their velocities in a very local level. So, it is so if you look at those interactions are essentially distributed over a large number of particles. So, if you look at its although we are making changes in each particle, but the effect overall effect is non-local. So, although changes are locally made in the velocity of each atoms, but if you look at it, they are done equipartition theorem around all 1000 atoms. So, the effects are propagated instantaneously. So, that really what we say is it essentially does not have lot of effect or artifact that is generated, because propagation does happen, it does take certain time, which we call equilibration time, but then it propagates instantaneously because the effect is non-local. And then we are also looking at interaction with the single heat bath variable dynamics, and we are looking at that dynamics can be a little bit strange, primarily because if you are doing a nicely vibrating system, you are putting an artificial rescaling. So, every time you rescale, you are essentially giving a different kind of velocity to the system. So, you see that velocity rescaling is kind of artificial change instantaneously made throughout the system, but then you wait for equilibration. So, every 100 time step, if you are making those changes, then of course, you have to account for those. And that is where in a constant heat bath situation, you will allow heat bath to rescale velocity on certain number of time steps, so that you do not see that artificial effects so pronounced. So, if you look at, I have given two references here which you may want to look at. One is from Journal of Chemical Physics 1984, Noze, Suichi Noze, who is the Japanese scientist, and we are looking at Walter Hoover, which is essentially we are looking at the physical review, which is 1985. W. Hoover, these are the Noze Hoover thermostat that we are looking at. So, now if you look at why do we need constant temperature, there are a number of reasons we want to do. Small system undergo large fluctuations like proteins. So, we are going to look at systems that we need to equilibrate very quickly. A large system also require that we have the constant temperature situation. So, if you look at the total energy, which is summation of kinetic and potential energy, that remains constant, but if you look at with no heat bath, it will drift, and that drift is towards the higher energy levels. So, you should think about why energy goes to higher levels and give it some thought on that. But if you look at NVE method, that will preserve the energy perfectly, but in long run there is some drift. So, I think that is where we need to have constant temperature MD. If you look at MD molecular dynamics methods, then we are now going to talk about three methods. One is the Anderson method. So, this is H.C. Anderson's method of 1980s Journal of Chemical Physics again. And so, if you look at in this case, this was a stochastic model. So, it was random at a random interval, the velocity of a randomly selected particle is replaced by a new vector chosen at the random from a Maxwell-Boltzmann distribution function. So, if you look at that is a stochastic model of rescaling the temperatures. So, if you look at these are different ways you can tweak the temperature in order to come up with NVT ensemble. So, advantage is that it is a simple way, it is a statistical way consistent with canonical ensemble, but if you look at the way it works in this case is drastic change to dynamics. So, this is where we are going to look at the Anderson method being stochastic, and Noze Hoover method that we looked at earlier is essentially deterministic, because it is changing the equation of motion, recasting it with a resistance term, so that you can adjust the temperature based on changing the resistance in the system. So, let me stop here. We are going to look at a couple of other methods and then look at what is the effect of these different algorithms in order to get to the NVT ensemble, which is the canonical ensemble. Thank you.